So this is going to start getting into just a little bit more of what we normally experience. Apart from static electricity on our clothes or something, we don't really do much with that. But then what we start to see is how this starts to move. So last week, we took a look and said that we had two charges. If we had a positive and a negative, we would have our whole electric field for those. And that's wonderful. That's great. And so this would be bringing that just out in the open, and we would have kind of those different pieces that we'd be dealing with. And so our electric field looks something like that. And that was what we focused on last week. By the way, if you haven't finished that up yet, please do that. Make sure that you get those things taken care of. Practice problems, lab, and quiz. If you are getting tangled up with the way your calculator works with that, don't worry as much, because as long as you're showing all the other pieces, you won't be penalized if you have a calculator issue. So this is what we focused on, and we looked at the way that if you have a charge in there, that it would respond within what else is out there. But what happens with electricity is, instead of having it affecting everything around it, essentially, we have a positive and a negative and just a wire running between the two. And because of that, we don't have all the other pieces around it. We don't have the charged particles around it. All the charged particles are our electrons, and they're in the wire. And so what it does is the electrons respond to the interaction of the positive and the negative. Electrons are negative, so they're pushed away by the negative charge and go here. And instead of having a single particle, a single charge, we have a whole line of them that goes through. That's what we get when we have electricity. So if we take and look at this in the way of a battery, we know that a battery has a positive and a negative charge. It has a positive end and a negative end, right? So if you go to put a battery in some device, you know that you have your positive and your negative, and you have to align it the correct way. By aligning it the correct way, you're making sure that the electricity and the electrons there are traveling in the correct direction. If you reverse it, then you can get some, then it goes backward and doesn't respond, doesn't work within the electronic device like you would expect. But so if we just had a positive charge here and a negative charge here, we could connect a wire in between them, and the electrons would travel along that wire. This just so happens that the positive and the negative are contained in a device, but the wire can bend. And so by hooking up a wire from one end to the next, you're able to get that flow of electrons. That's what would happen. That's what we use in order to power different devices. Now, here's the thing. If you just take and put a wire on there, you're going to get a really big flow of electrons. It's going to overheat it really quickly, and the battery will die out. Oh my goodness, I have the yawns. The battery will die out quickly, so you don't want to do that. But it's essentially what we're looking at. So in doing this, there's some vocabulary we need to talk about. First of all, the idea of electricity. It's just a flow of electrons. It has a flow of electrons. We have a whole bunch of electrons moving from one place to the next. As the electron parade is going by, you have your electricity, and it can be used to power different things or get things to go. And so with this, we have some different vocabulary that helps us understand what's going on. First of all, we have our current. And our current is represented, I know this is weird, it's represented with an I. And it is a measure of the flow of electrons. Say a measure of electron flow. So when you have the electrons going by, they can go by quickly, they can go by slowly, you can have a lot going by at one time, you can have a few, whatever that looks like, the current will give you that measurement for that. Current is measured in amps. Technically it's amperes, A-M-P-E-R-E. We refer to it as amps. And 1 amp, oh, excuse me, goodness gracious, is equal to 1 coulomb per second. And so when if we're going to talk about coulombs, if we're going to talk about charge, remember you have a whole lot of electrons in a coulomb, and then coulombs to amps just gives us something to talk about that keeps it a little bit more concise. So 1 amp is 1 coulomb per second. You guys, I need to wake up. And then we'll use that in the discussion of current. Think about a river. When we talk about a river, a current in a river, we're talking about how much water goes by per second. Here we're talking about how many electrons per second. If you have a really a strong current in the river, you have a lot of water going by. If you have a strong current here, you have a lot of electrons going by, so a higher charge going by. We also have voltage, represented with a V. It's the potential difference and we'll talk about that in a minute. And voltage is measured in volts, also a V. Yes, this is the one time it all aligns. Voltage starts with a V. It's measured in volts, which are also a V. Your variable and your units are the same on this one. The one time it works really, really nicely. Potential difference works like this. Think about a pen. And think about gravity. If I put potential energy into this, I'm lifting it up and I've added potential energy. I'll lift it higher, I have more potential energy. And the bigger the difference, the faster it'll go as it gets to the bottom here. The same thing works with voltage. The bigger the difference between the positive and negative, kind of the bigger the push, the faster it can go from one place to the next. And so when we have 9 volts, we have a different potential difference than if we have like a AA or AAA is 1.5 volts. So it's the difference of like dropping it from here or dropping it from here. And then we have our resistance, represented with an R. And it slows the current and it uses the power. So the current, a combination of the current and the voltage gives you the power that's there. When you put resistance in there, it's going to slow the current and use the power up. So it's part of what you have. If you have a circuit that has a higher resistance in there, the overall current will be lower. So resistance slows the current, uses the power. Again, if we think of our river analogy and we put a dam in there to generate electricity, well, it's going to slow down the overall current of the river, and it's going to use up some of that power that is present in the river. And that dam then would bring it elsewhere, but that's sort of the overall piece that it does. The last thing that we'll be talking about and we have talked about it before is power. Power is represented with the P, and it does the work, energy, something. It might turn on a light. It might turn on a radio. So if you turn on a light, you have light energy. If you turn on a radio, you have sound energy. If it spins a motor, you have mechanical energy. So it does something with the electricity, and it allows it to do whatever we want it to do here. Power is still measured in watts, represented with a W. And I'll actually give you a more concise table of this in a little bit, but this has the variable, what it is, and then the unit represented here. So if you want to take a screenshot of that, go ahead and do that. One of the things that we use when we're doing this is called a schematic. And a schematic is your representation, your visual representation of the circuit. So what it looks like based on how your components are in there. And so I want to give you a few of the things that we have here. This one is the battery, or your power source. It will be measured in volts. It's how many voltage, what voltage you're able to get here. You'll have something that looks like this. This is a resistor. Anything that's going to use that resistance. Resistance is measured in ohms. This is another form of a resistor. It's a circle with an X through it, and it's a bulb. So it's a light bulb of some sort. It is also measured in ohms. And the last one sometimes shows up, not always, and it's just a switch. And that just indicates that you have something that can turn off and turn on. We'll use these components to visually represent the way that a circuit is structured. So if you want to take a screenshot of that or write it down, do that, please. I'll be erasing it in just a moment. So what this might look like, let's take and use an example here. I have a 9-volt battery and just a bulb. I took, at school, we cut up a whole bunch of strings of lights just to have these little bulbs on here. So if you look at your battery, you have your positive and your negative charge on it in what you have up here. And so if I take and I touch one end of my bulb to the positive charge and one end to the negative charge, that flow of electrons is created and I can turn on my light. It goes like that, off and on. I know the iPad can sometimes make it not quite as visible as you would experience here. But just that simple connection allows the electrons to flow from one side of the battery to the other, and then therefore causes it to light up. So how would we draw that as a schematic? Well, as a schematic, we would take and we would draw our bulb. We put that in here, connect it to the battery, and that would be our simple schematic representing what we have when we have it up here. Now it doesn't, the lines are usually nice and they're either parallel or perpendicular to each other. So these two are parallel here and then perpendicular, perpendicular. But it's representing what's happening. You have a battery and a bulb that's connected. And so what we have then is with this, we have two different equations. The two equations we have, first of all, are V equals IR, where V is the voltage, I is the current, and R is the resistance. So if I have a 9-volt battery, by changing the resistance, I'll change the current. If I have more resistance, I'll have less current. If I have less resistance, I'll have more current. If I add voltage, I can change what I have over here. So depending on what you have and the way it's set up will depend on what you can get out from there. So in this relationship, we have V equals I times R. The second equation that we'll be using this week is P equals I times V. So the power is equal to the current times your voltage. So if you need more power, you can get that in one of two ways. You can either have a stronger voltage, or you can have a stronger current, or you can have some combination of both. But we're looking at these two equations for what we're discussing this week. So in the way of these equations, they're both pretty straightforward. You don't have a lot of variables. You don't have a lot of rearranging to do. If you rearrange, it's just dividing by one thing or the other. If you prefer the triangle method, you have V, I, and R, P, I, and V. So if you want to take a screenshot of those things that we have on here, please do that. Again, for this week, these are the two equations that you're working with. Any questions on this so far? I'm going to do a couple of examples, and then I want to walk through what you're doing for your lab and for your practice problems, and then we'll be wrapping up. So I'm going to take this now. Let's say we have what we had before with a bulb and a battery. And let's say that our bulb is 5 ohms of resistance, and we'll say that we have a 9-volt battery. Probably pretty similar to what I have here. So we want to solve for our current and our power. So we know that our resistance is 5 ohms. Our voltage is 9 volts because that's what's given in our schematic here. We're going to solve for the I, and we're going to solve for the power. So we can use V equals IR. And if we're solving for the current, we'll divide both sides by R. So we have I, our current is equal to our voltage divided by the resistance. And we have 9 volts and a resistance of 5 ohms. And so we have 1.8 amps. So assuming that the resistance on the bulb is 5 ohms, connecting it to a 9-volt battery would give us a current of 1.8 amps. These bulbs are definitely not created to have 9 volts across them. That's why it's really, really bright, because they're usually in line with a whole other string of bulbs there. So we have 1.8 amps based on the situation that we have here. With that, then we can calculate the power, P equals IV. And so we'll take the current that we just calculated, 1.8 amps, times our voltage of 9 volts. And that will equal 16.2 watts. Again, the equations themselves are decently straightforward with what we're doing. It's getting the understanding of what's happening with the different parts, how they're conceptually related, and then how they're mathematically related. We'll say example 1 on this one. Any questions on that one? You can screenshot it if you'd like. Go on to the next one. We'll say for example 2, we'll say a similar structure here. This one, we'll say that we have a 12-volt battery. And we're going to say that we have a current of 0.5 amps. So all the way through, we have our 0.5 amps. The voltage is used up here and comes back empty, but the current stays through the same all the way through. So we can say that our current is 0.5 amps and that our voltage is 12 volts. So let's figure out the resistance here and the power. So we can say that R, we rearrange V equals IR, we can say R is equal to V over I. And then we can set that up and we have 12 volts divided by 0.5 amps gives us 24 ohms. So the resistance that we have in this bulb here is 24 ohms based on what we have here. We can get the power. P is I times V. So now I'm going to take my current of 0.5 amps times my voltage of 12 volts. 0.5 times 12, power here is 6 watts. So depending on what I have and depending on what I'm looking for, I can use this combination of equations to figure out where things are and what we're doing. So again, if you want to screenshot that, they're all there together. Let me take this off. There we go. Any questions on either of these? Before I go on to showing what we're doing for the stuff this week, I want to just put up a quick little chart that you can use as a reference when you're looking at problems and figuring out what pieces you have. So we have the variable and then the unit. So we have voltage is represented with a V and measured in volts, also represented with a V. We have current represented with an I. I know that makes no sense. Somewhere along the lines within the scientific community that was decided upon. And it's measured in amps. Resistance represented with an R, measured in ohms, like that. And then power represented with a P, measured in watts. So keep that handy while you're working on it so you can reference the different pieces that you're looking at. And then if we want, we can add V equals IR and P equals IV. Both of those pieces there. Write that down or take a screenshot of it. I'm going to also then go ahead and move to Schoology real quick. I want to talk through what we're doing for our lab this week.
Could you go back to that for a second?
Yep, I can. There we go. So we're going to talk in a moment about what we're doing this week. We'll look at our practice problems, and we'll look the practice problems that we're looking at are, let's do this, courses, practice, or sorry. We're in week 2 here. And so the practice problems that we have a quiz that I'll post up later today. We have our practice problems for Ohm's law and power. Practice problems that we have here are pretty straightforward. There's just a couple of them. So the first 3 are just sort of asking some overall questions. On number 1 and 2 of your calculations, it's asking you to show something about, it gives you coulombs and it gives you current, and some of it might give you a time. And so keeping in mind that 1 amp is equal to 1 coulomb per second. So on numbers 1 and 2 in your practice problems, you'll need to keep this relationship in mind. And I'll give you that for right now, and then we'll go into it on Friday. And then for the rest of them, you're using V equals IR and P equals IV, or some combination of those. So that's the first part that you're looking at. When it gets to your lab for this week, normally what you would do is you'd be coming into class and I'd have a whole bunch of different stations set up, and you'd be measuring the current in various devices. And so we have these 10 different objects that you'll measure. They're each connected to a 9-volt battery, and you're going to measure the current that's in there. Obviously, we can't do that. There's not a way to just magically do that. So I have a video here, and I took it from one of them that we did during school at one point. And so when you click on that, what it'll do is it talks you through the basics of something called an ammeter. And an ammeter is a device that measures current. You can see that there's some wires. There's a 9-volt battery connected here. And then over here you have your tennis ball with some light bulbs on it. And so when you connect it to the battery, the light bulbs go on and you can measure the current that's going through the ammeter. So it sort of gives you that setup, then it gets a little bit closer to the ammeter to show what you're measuring here. There's 2 different scales, one that goes from 0 through 5 and one that goes through 0, then it goes 0.2, 0.4, 0.6, 0.8, and 1. That smaller scale is the one that we'll be using. So if it's, falling along any line, these little lines that follow along here are 0.02 amps. So if you look at this example here, you're at 0.6, 0.62, 0.64, 0.66, 0.68 amps. And so that's what you would be writing on that. Now, the video is not super clear, and I cleaned it up a lot, but it's not super great. So what I did in setting it up is I got it here, and so it'll tell you what you're measuring. Then it'll show you the measurement. You'll see the needle coming up when it's connected, and then it actually gives you the measurement there. So instead of having people be all stressed out about it, I just decided to show it. So headphones, you see the needle jumping, and then it'll tell you where that was on there. So 0.06 resistor. Again, it'll show you the needle jumping, not very far on this one. It's a pretty big resistor. Touch it there. You see it jump a little bit, and then it will tell you what's on there. So again, it's not anything that's super high tech in this. It's hard, particularly with this, to be able to get the other pieces, just all the pieces together that we would normally have. So it's sort of the best way we can do it. So what you'll do is you'll take that number that's given for the current there and you'll write it in here all the way down for each of the different objects. Then you'll calculate the resistance. You'll show one example of your resistance calculation here. You'll calculate the power. You'll show one example of your power calculation here. And then you can put the rest of the pieces in there. Then you're just answering the questions about most resistance, most power, least resistance, least power, and then a general relationship about what you're seeing there. And so as you're doing that, you'll get the information off of the video, you'll put it into the lab, and then you'll answer the questions. So hopefully it's pretty straightforward for what you need to do on that. Again, with this topic, it generally isn't super crazy in the things that you're needing to do. However, keep in mind that it's building a base to be able to understand what we're talking about in the next couple of weeks easier. Lastly, in your videos and summaries, there's a video that goes over what we talked about just now, and it also goes through some different examples. There's also an overview that's just a written page of what we're talking about. So it has your definitions, your symbols, the equations, the triangle form of those, and then an example. So if that's helpful for you to have up while you're working on things, sometimes being able to look and reference that can help move you along as you're going forward. And there's one of those in for all of the topics that we have. Again, I'll put our quiz up sometime later today, and you can get that going sometime before Friday. I think those are all of my things. Does anyone have any big questions before we wrap up here? Anything that would benefit the whole? All right, so this week, two main things. One, you're working on getting your practice problems done, your lab done, with the understanding that you're building a base for what we're doing over the next couple of weeks. Two, if you have not completed something from last week, please wrap it up and get it in. If you're having a hard time with your calculations, make sure you're showing all your work nice and clear, and that'll be okay. You'll be okay with that. If you're having trouble with calculations, there's a couple of calculator videos up there. They're in the updates that you can watch and follow and use as needed in that way. So whatever works best for you, that's what you need to follow and do, but mostly get your stuff in, be moving forward, be getting things wrapped up so that we're in good shape continuing to move forward. So I'll hang on if you have any other questions. Other than that, thank you for being here today. Thank you for continuing to work hard and move forward, and I will see you on Friday. Bye-bye.